Welcome back to the second module of this lecture on strength of material. In Module 1, we laid the foundation by understanding the basic principles of force equilibrium, stress and strain, composite bars, temperature effects, and internal forces such as bending moment, shear, and torsion. In this second module, we will build on those fundamentals and focus on advanced analysis techniques, including stress transformations, Morse cycle, failure theories, strain energy, applications of these principles in structural design and safety. Let's begin with an exploration of how stress behaves in different directions. Lecture 1: Stress transformations. In engineering, it's common to evaluate how stresses change when we observe them from different directions or orientations within a material. This is especially important in structures that are subjected to complex loads. Stress transformation refers to the process of determining normal and shear stresses acting on a plane at any arbitrary orientation. For example, consider a rectangular block subjected to forces on its faces. The normal stress acts perpendicular to a surface, while shear stress acts parallel. As we rotate the observation plane, these stresses redistribute. Stress transformation is important because failure may not occur along the original planes of loading. Rather, it may occur along some inclined plane where the stress is maximized. Engineers must understand how to calculate stress components at various angles to predict where and how failure might occur. Lecture 2: Morse cycle, a graphical tool. To simplify the visualization of stress transformation, engineers use a graphical representation called Morse cycle. Morse cycle is a two-dimensional diagram that illustrates the relationship between normal and shear stress on different planes within a material. Instead of solving equations manually for each orientation, the cycle allows you to identify maximum and minimum normal and shear stresses graphically. Morse cycle is particularly useful for finding principal stresses, the maximum and minimum normal stresses acting at zero shear, determining maximum shear stresses, understanding the orientation of principal planes, interpreting complex stress states quickly and clearly. This tool is widely used in structural design, pressure vessel analysis, and mechanical component evaluations to ensure safe and efficient material performance. Lecture 3: Failure theories in materials. Materials do not fail simply because they are loaded. They fail when the internal stresses exceed certain thresholds that the material can no longer withstand. This brings us to the study of failure theories, essential for determining safe load limits. There are several major theories of material failure. Maximum normal stress theory. This theory suggests that failure occurs when the maximum normal stress in the material exceeds the tensile strength. Maximum shear stress theory, also known as the Tresca criterion. According to this theory, failure occurs when the maximum shear stress in a component exceeds the shear stress at yield under a simple tensile test. Distortion energy theory, or also called the von Mises criterion. This theory is based on the distortion energy in the material and is particularly applicable to ductile materials. It states that failure occurs when the distortion energy reaches a critical value. Each theory applies to different materials and situations. For example, brittle materials like cast iron often fail in tension, so the maximum normal stress theory may be more appropriate. In contrast, ductile materials like steel often yield in shear, making the maximum shear stress or distortion energy theory more relevant. Choosing the right failure theory helps engineers design safe structures that can handle real-world conditions without breaking or yielding. Lecture 4: Application of failure theories. Understanding failure theories isn't just about academic knowledge, it's about practical engineering design. For example, in designing shafts that transmit torque, engineers use the maximum shear stress theory to determine the allowable torque before failure. In pressure vessel design, Morse cycle and principal stresses are used to identify the critical stress paths. When selecting materials for machine components, engineers apply the distortion energy theory to predict whether a material can endure complex loading conditions. All of these applications ensure that products and structures are safe, durable, and reliable, while also being cost-effective. Lecture 5, Introduction to Strain Energy. When a material is deformed under load, it stores energy. This energy is called strain energy. It represents the work done by external forces in deforming the body. If the material behaves elastically, that is, it returns to its original shape when the load is removed, all this energy is recoverable. But if the load exceeds the elastic limit, some energy is lost due to permanent deformation. Strain energy is important in areas such as spring design, impact and crash analysis, earthquake-resistant structures, fatigue and vibration analysis. Understanding how much energy a material can absorb before failure is critical in designing components that experience dynamic or fluctuating loads. Lecture 6, Strain Energy in Axial, Bending, and Torsional Loading. Let's explore how strain energy behaves under different types of loading. Axial loading. When a rod is pulled or compressed along its axis, the material stores energy due to elongation or compression. This is common in trusses, columns, and tie rods. Bending. Beams under bending moments also store strain energy. This energy depends on the type of load, the material properties, and the cross-sectional shape. Engineers calculate this when designing bridges, cantilevers, and building floors. Torsion. Twisting a shaft stores strain energy in the form of rotational deformation. This is especially important in the design of drive shafts, gear systems, and wind turbines. Understanding this concept helps engineers select suitable materials and determine the size and shape of components to ensure that they can safely store and release energy without damage. Lecture 7, Strain Energy in Failure and Impact Analysis. Strain energy also plays a key role in analyzing failure due to sudden or impact loads. For example, when a hammer hits a nail or when a car hits a barrier, the components involved absorb energy in a very short time. Engineers use energy methods to predict how much deformation will occur, whether the material will break, and how to design components to withstand such impacts. In safety-critical systems such as airbags, crash barriers, and protective gear, strain energy calculations ensure that energy is absorbed efficiently and safely. Lecture 8, Real-World Applications of Strength of Materials. To wrap up this course, let's examine how the knowledge of strength of materials is applied across different industries. Civil engineering, designing buildings, bridges, dams, and towers. Mechanical engineering, designing engines, machine parts, drive systems, and turbines. Aerospace engineering, creating aircraft structures and fuselage components. Biomedical engineering, developing prosthetics and surgical implants. Automotive engineering, ensuring safety in vehicle design. In all these applications, understanding how materials behave under stress, strain, temperature, torsion, and impact is essential. Engineers use the principles we have studied to ensure that every structure, component, and system is efficient, safe, and reliable. Conclusion and summary of Module 2. In this module, we explored the advanced topics of stress analysis and material failure. Specifically, we covered stress transformation and how stress behaves at different angles. Moore's circle for graphical interpretation of stress. Failure theories including maximum stress, shear stress, and distortion energy. The importance of selecting appropriate failure theories based on material type. Strain energy and its application in axial, bending, and torsional loading. The role of strain energy in impact and failure analysis. Real-world engineering applications where strength of materials is critical. These topics bring a comprehensive understanding of how materials respond not only under static conditions but also under complex and dynamic loads. Closing message. You have now completed the 2-module lecture on strength of material. This course has equipped you with both theoretical knowledge and practical tools to analyze structural elements and predict how materials will behave under various forces and conditions. Always remember that safety, efficiency, and innovation in engineering begin with a solid understanding of how materials carry loads, deform, and fail. Thank you for your attention, and I wish you success as you apply this knowledge in your studies and professional engineering practice.